couldn't figure out what function the Taylor series represented. So just taking a step back, you guys, for these questions on series, they're going to give you either the function, the series, or both. Okay, so we've seen some for responses where they give you what f of x was, they give you what t of x was, and then you work with one or the other. We've had some instances where they give you the series, and then you have to figure out what function did it represent. And then this one, it's like the only thing they gave you guys, as I trace this out for you or highlight this, the only thing they gave you guys was this series. And notice that they reference an f, but there is no function that you guys could possibly work with. So whenever that's the case, it's like the worst case scenario where you don't have a function to deal with. They're not asking you guys to come up with the function. You're just working with the series. Okay, and the series becomes everything for questions on the function itself, because that's the only thing you guys have to work with. That's the approximation of the function. And then we really just work with that from there. Okay, so let's say you guys had this Taylor series. What I'm going to encourage you guys to do for your notes purposes is that if you kind of had no idea where to start with this, you're going to write out, well, what is a Taylor series, like general term? Okay, so in this case, the formula for it would have been f of the center f of a. Then we would have had f prime of 2, the first derivative term, over 1 factorial x minus 2 to the first power. So this is me just writing out, this is what a Taylor series should be. So x minus 2 squared, and I'm going to stop there. And we know that there's a third one after that. Okay, and as we start to match up, okay, well, f of 2 is represented by the constant value. That should be what f of 2 is. The first term in your series is the function evaluated at 2. So the answer to f of 2 lies within just looking at the series itself and then finding out what part of it is it referencing. So the answer to f of 2 is 7. Now f double prime of 2. Okay, so f double prime of 2 happens to be also within the formula itself right here, where you guys have this expression represents the second derivative at 2 over 2 factorial. So here's what I would like you guys to type out in the chat for me. What would you guys set f double prime of 2? So for part A, f double prime of 2 over 2 factorial, what is that equal to? Based off of the series that you guys have, what should that be equal to? And just as I'm looking at some of the answers, remember that this is referring to the second derivative at 2 over 2 factorial. Okay, good. So the majority of you guys have it. If you take a look at this, I think it's because of the way that I had it set up. So many of you guys were just lining this up. So you were just saying, oh, this is f of 2, this goes with this, and this goes with this. If you pay attention to the exponent, the squared term is the one that we're looking for. So it should be the -9 that is equal to that. Notice also that this Taylor series skipped over the first derivative. Okay, and that's going to be significant for part B. So for part A, after you guys figure out what constant to set it equal to, 2 factorial is just 2, multiply both sides by 2, you get the second derivative should be equal to -18. Okay, and so that's a roundabout way to get to that answer. I want you guys to be comfortable doing that, to understand that the coefficient in front of each one of your x minus a term is really representative of the derivative over a factorial, because there's a lot of play on that type of questioning on the multiple choice as well. Okay, any questions on part A? That's a really important one. And then also, I didn't write down the answer, but f of 2 is equal to 7. Okay, so kind of piggybacking off of part A, for part B, they're asking you guys, is there enough information to determine whether F has a critical point? So now they're tying in things from first semester. So in the chat, without thinking of series, thinking back to Calc A, can you guys tell me what would be required of you to determine that something has a critical point at x equals 2? What does that mean? What has to be true? If there's a critical point at x equals 2, what would have to be true? Go ahead and type that into the chat. Good. Okay, so we've got that if it is a critical point, that f prime of x has to be equal to 2, f prime of 2 has to be equal to 0. Okay, the first derivative at 2 would have to be equal to 0. Go back to the Taylor series. Is that true? Is the first derivative equal to 0, according to what you guys have in your Taylor series? Okay, and so I know when I initially wrote it out, some of you guys were tricked in the sense that you thought these two lined up. Well, if we look back at our Taylor series, you have a constant, and then what technically should be next is the first derivative term, but we skip over that and we get the second derivative term. So that means we're missing the first derivative term. The only time that you're missing that is if you had 0 for the numerator of your first derivative. And so we can make a conclusion that since f prime of x, f prime of 2 is equal to 0, we have a critical point at x equals 2. Okay, the follow-up question would be, if so, determine whether f of 2 is a relative max, a min, or neither. Since we don't have a function to work with, an actual function, it's not like we can come up with the derivative and test points around it using the first derivative test. So what else can you guys use besides the first derivative test to determine if you guys have a max or min? What else from first semester could you guys use to determine if something's a max or min? Okay, so back to first semester, we had two tests, right? We either had the first derivative test, which required a sign chart, but think of what you guys need for the sign chart, because someone said if we did the sign chart, we would have 2, and then we would need to pick test values and plug it into the derivative function, but we don't have the derivative function to work with. So the next test that you guys would move to is the second derivative test. Okay, according to the second derivative test, you just need what the sign is of the second derivative at the point you're testing. So in this case, what is f double prime of 2? Do we have that already? If we look back at, yes, if we look back good at part 1, we have that it's less than equal to 0 or less than 0. Okay, so do you guys have a max or min or neither here? Okay, so the function is concave down, exactly. So those are the things you're going to mention when you're doing second derivative test. You're going to mention the sign of the second derivative. You're going to mention it's concave down, and that therefore you guys have a max. Okay, looking back now, now that you guys have seen the way that this was asked, series serve a purpose in that if you don't have the actual function with, you have an approximation, you're going to treat that as though that's your function, and you're going to be able to answer questions like B, where it had to do with first semester stuff, using the actual series, and you're thinking of the series as your function. Okay, for part C, I bet you many people missed this question, except for maybe the first part of it. So don't feel so bad if it went over your head for part C. What if I did the first derivative test and took the first derivative of the given series, then plugged in values and concluded it was a relative max? That also works as well with this part of it, as thank you for mentioning that. Some of us, instead of using the coefficients like I did, also did the same thing and took the series as the original function and then took successive derivatives to get these answers. And so that's what someone did, and applied the first derivative test as well on this. And that, I think that would have been fine, as you're not going to see that in the justification, but that should be okay to do as well. So for part C, even though you guys might not get the entire question correct, you want to make sure that you guys answer what you guys can. So when you look at part C, you're going to see use T of X to find the approximation of f of 0. That should be easy. There's nothing but plugging in for that one. Okay, so if you guys can all just make sure you do that part for me. If you didn't get to see, can you guys go ahead and find out what f of 0 is so T of 0 should be f of 0. And so that's literally just, using your series as how you're going to evaluate this expression at 0. Okay, the second part of it is purely conceptual. I really doubt many students got it this year when they asked this question. So pay attention to what we just did. We used T of X to approximate F of 0. The follow-up question was, is there enough information given to determine whether F has a critical point at X equals 0? And they start to ask the same questions that they did for part B as for T of 2 as they did for T of 0. So now if we take a conceptual stance on this and we think about 2 and 0, okay, 2 happens to be the what of this series, you guys. 2 happens to be the what. There's something major about 2 that's different from 0. Okay, and conceptually, yes, 2 is the center. Okay, conceptually, the center is always a perfect approximation. At worst, when you're given a series, it's always a perfect approximation at the center, but the more you guys move away from the center, the worse off the approximation. Now, if we're going to start to use these series to represent functions and make conclusions about the original function, we want to make sure that we come up with the appropriate series for that conclusion. So when I was answering part B, I could answer questions about relative maxes and mins when it was at the center. But when you move away from the center, it's no longer a good idea to make conclusions about things like that you're like making an extension about. Like, so we're going to extend ourselves and use this. Can we use this to make a conclusion about maxes and mins at 0 when that's not the center? And the answer is no, you can't. The better idea would be to build a new series that's actually centered at 0, and then use that. If we're going to use that to make a conclusion about what's happening at 0, we want to make sure we come up with the best series for that. And so the answer to this for the rest of it is that no, it wouldn't be a good approximation because it's not where the center is. Okay, so part D, follow-up question to that is, okay, so even whether it was good or not, we used it for an approximation. We used it to come up with the function at 0 is -5 or is about -5. Now they're saying, can you determine what is this error in using the series that you just did to approximate x equals 0 or the function at x equals 0? So let me go ahead and have you guys highlight or underline this. This isn't going to be the first time you're going to see something written like this. Okay, so it says the fourth derivative of f satisfies an inequality of the fourth derivative, the absolute value of that is less than or equal to 6. Okay, and so there were many Lagrange error bound questions where, like, let's think of sine and cosine. I accepted both answers on the quiz where some of you guys did like sine of the x value that you're approximating at over whatever factorial it was, or I also accepted the general response that, you know, as you take successive derivatives, the maximum was just 1 for sine or cosine or any one of the functions that end up being the derivative functions. Here, they remove that part that's ambiguous and they just give you guys what the maximum derivative is. So what you just underlined, that statement is saying that the fourth derivative is going to attain a maximum of 6. And so that's going to be easy for us to then just use and plug into the Lagrange error bound. So for part D, when I write out my maximum error, I'm going to say that it's less than what it should be, the fourth derivative at some value z. Again, it doesn't matter what that value is, over 4 factorial. By the way, we say 4 because if we look at the Taylor series, it ends at 3. So we know the Lagrange error bound is going to be tied to the fourth. So we're going to write the fourth term of this Taylor series, x minus a to the fourth power. That is the Lagrange error bound. You have absolute values around it because it can't be any more than this, the positive value being error. So we go back, we plug everything in that we have. So we know the maximum derivative is 6. So 6 over 4 factorial. I'm going to leave x right now, and then we know the center is 2. What do you guys plug in for x here? What do you guys plug in for x here? Okay, it's whatever you guys want to approximate, right? We're trying to find the error for 0, x equals 0. So we're going to plug in 0 for x. Okay, and then we're going to take the absolute value of the whole thing, which ends up being positive anyways. And I believe the answer was, let's say you guys simplify this out and you get -1. oh, sorry, you get +4. And when you guys think back to that one activity that we did where we were approximating what the sine of x function was, and then we came up with the series, and then we came up with the error, and we kept subtracting the two. So the very last part of this question asked, use Lagrange error bound on the approximation by to f of 0 found in part C to explain why f of 0 must be negative. So if you guys think of like the actual being better approximated by whatever let's say you initially had the approximation. Technically, if you guys add the error to it, oops, I meant to write error there, you would get closer to what the actual approximation is. So anytime you're off by something, if you add that error back, it should get you guys closer to what the actual is. So our approximation from before was -5. So if we add our error, it would ensure that this value at t of 0 is actually still negative because you get a difference of -1. Okay, and so even though we added the error back in, we still got a negative number, and the question was just, how do you know that it's still negative? So I'll show you guys I think we're out of time actually, but if you scroll down, I included the scoring guide for this down below here. You might not want to score this one, but this was just purely practice and just getting you guys used to seeing some of the things. So some important notes to make that I see recurring on AP tests is the idea of working with the coefficients is something that you want to be aware of. Working with a series in place of a function if we don't have the actual function. And this expression for the Lagrange error bound where they have an inequality and they tell you that the maximum the derivative attains is this, like just telling you guys straight up what the actual derivative is, the maximum for that derivative. Those are going to be some themes that you see in the questions that they like to ask. So I know this was a tough one. It's our first time seeing it phrased a certain way, but hopefully going forward, it'll get a little bit easier as we do it. And then I'll hit you guys with 2005, which